Everybody knows what knots are. They keep our shoes tied and serve endless other practical uses. Knots are nearly everywhere and are used to hold just about anything together. There are all kinds of imaginative and inventive ways to twist, intertwine, and combine strands of yarn, rope, string fiber, virtually anything that comes in strands, including cellular DNA. Scientists who study cellular DNA find knots of interest because strands of DNA tend to form tangles or knots. In fact, DNA knots are very similar to the ones we tie every day. Square knots, granny knots, figure-8 knots, and trefoil knots. The branch of mathematics that studies knots, tangles, and their properties is called topology. Topology is actually the study of objects that remain the same when you deform them. In other words, when you rearrange a knot and analyze the structure of its crossings and intersections, you are reviewing its topology.
And a yellow edge.
Dr. Nicholas Cozzarelli of UCLA at Berkeley is a molecular biologist who studies the relationships between knots and DNA.
The DNA of all organisms has a discrete topological structure, and that topological structure has to be maintained, and so therefore one of the things that scientists are interested in is that why is it that the topology of DNA has to be maintained? What does it do for the cells? Why is it important? And the other reason why I'm interested in DNA topology is that it's a terrifically useful tool for understanding enzymes that change the structure of DNA. The reason is that many of these enzymes act extremely quickly and in very small places, and we can't see directly what the enzymes are doing. But we can tell what the enzymes did because they changed the topology of the DNA. So it forms a permanent record of the action of enzymes on DNA.
In topology, a knot is defined as a three-dimensional closed loop that crosses over itself in a way that cannot be untied. Using this definition, mathematicians find that not everything that appears knotted is in fact a knot. Because knots are three-dimensional, it is sometimes difficult to observe the exact composition of a knot without looking at it from all sides. And even then, its structure isn't always apparent. On the other hand, a tangle is just what you would think it is, a confused bundle or jumble whose composition is not always apparent. In a tangle, one might find loops can be confused for knots. If the ends are free, then it can all be unraveled, and therefore is not a knot. One way to tell if a tangle is a knot is to see if it can be deformed to make a circle. Circular loops without intersections or crossings are sometimes referred to as trivial knots or unknots by mathematicians. Here is a very strong knot that is often used by sailors, called a girth hitch. But when removed from this pipe, we can see that it isn't actually knotted at all. While DNA knots can occur in a wide range of patterns, most of our everyday utility knots are in fact unknots. Out of practicality, they are designed to tie an object to another object and then be easily undone. The ends of the strands need to be free for ease of tying and untying. It seems that it is natural for strands to form knots, loops, and tangles. Watch what happens when we drop a long coil of climbing rope. A tangle is formed automatically. In fact, the longer the strand, the greater the mathematical probability that we will find a knot. It's one of the reasons that DNA is knotted, because DNA is extremely long. Scientists are using knot theory to find ways of accurately decoding the topology of a knot and describe it in ways that permit easy classification and comparison to other knots. Here is one approach to classifying a type of knot found in DNA research. These are two micrographs, or pictures taken from an electron microscope. These knotted strands of DNA have 3 crossings, which makes them trefoil knots. Are they the same topologically? Let's make believe we're walking along the knot, and each time we hit a crossing, we draw an arrow. The arrow is interrupted to show that one strand goes under the other. We now have 3 sets of arrows, and there is a simple rule we can apply. Look at the fingers of your right hand and your left hand, and the way the fingers cross the thumb. The left hand is a negative sign. The right hand is a positive sign. By observing the direction of the crossings in relation to the crossing of our thumb, we can now say that while these DNA knots appear similar, one is a negative trefoil, the other is a positive trefoil. This is just one approach to comparing and classifying knots using principles of topology. Knot theory is gaining wider acceptance in the scientific community as scientists try to find new ways to unravel some of the mysteries of DNA by determining whether a tangle is a knot or not.